Good afternoon, respected organizers, session chairs, academicians, researchers, industry professionals, and dear friends. I'm Engineer Aditya Singh, ISDS M.ASC AMIE. I've been an independent researcher, editorial review board member in 6 American international journals, reviewer in 10 American, 6 Singaporean, 1 Indonesian, and 1 Swiss-based international journals at the moment. Alumni mentor registered by Amrita University Alumni, Amrita Vishwavidyapeetham, India, think tank expert at Beijing Zhongshuan Electric Power Energy Big Data Research Institute, and ex-research mentor at Academy Nova World, Kalipur, India, and ex-alumni mentor LPU. Today's topic is the systems of circular construction and climate responsive leading a MCD framework. Outline in today's presentation, introduction, literature review and research gaps, circular economy, and other topics will be considered. Introduction. The construction industry is undergoing a major transformation driven by climate change, resource scarcity, rapid urbanization, and increasing sustainability expectations. Traditional construction has largely followed a linear economic model characterized by resource extraction, production, consumption, and disposal. However, this model has become increasingly unsustainable because it generates significant material waste, greenhouse gas emissions, and environmental degradation. Circular construction and climate responsive infrastructure provide an alternative systems based approach. However, implementing these approaches require balancing multiple and often competing objectives, making multi criteria decision making an essential component of sustainable infrastructure planning. Background. The construction sector plays an essential role in economic development, but also represents one of the world's most resource-intensive industries. According to UN Environment Program and Global Alliance for Buildings and Constructions, uh, buildings and construction account for more than one-third of global energy and process-related carbon dioxide emissions, uh, which consume vast quantities of raw materials and generate substantial volumes of construction and demolition waste. International research increasingly advocates for circular economy principles where materials remain in productive use for as long as possible through reuse, repair, manufacturing, recycling, and recovery, which is sustainable in the long term, as the old method is not suitable uh, as we are progressing over the years and urbanization is increasing, as well as the demand for infrastructure is also uh, being increased because of the population increase and migration of people to cities for job opportunities. Then, at the same time, climate change requires infrastructure capable of adapting to higher temperatures, flooding, droughts, sea level rise, and more frequent extreme weather events. These interconnected challenges motivate the development of integrated systems combining circular construction, climate responsive design, and evidence based decision making. Literature review and research gaps. roughly 40 published papers where the recently published studies were taken into account. There were a number of gaps which were found, which includes relatively few integrated frameworks simultaneously combine circular economy principles, climate responsiveness, governance, and multi-criteria decision making. Then digital twins and AI remain underutilized within circular construction decision support systems. And standardized indicators for measuring circularity performance remain limited, and empirical evidence from developing economies remains comparatively scarce despite rapid urbanization and infrastructure expansion. Then greater integration is required between life cycle assessment, life cycle costing, climate risk assessment, and decision support methodologies. Then the question comes the relevance of this study. Through this study integrates circular economy, climate resilience, governance, and MCDM, and it supports evidence-based infrastructure decision making. Plus, it provides a system approach for sustainable infrastructure planning to be done effectively, and it emphasized the opportunities to integrate AI, life cycle assessment, digital twins, BIM, uh, and as well as life cycle assessment into the future frameworks of MCDM. Circular economy, circular construction applies circular economy principles throughout the complete infrastructure life cycle rather than considering buildings as temporary products eventually discarded. Circular construction views infrastructure as long-term material banks whose components retain value throughout multiple life cycles. So it begins during the planning by considering future adaptability and resource efficiency, and the design emphasizes modular construction, durability, design for disassembly, and material recovery. Then the construction focuses on maintenance strategies, uh, which extend the infrastructure service life. At the end of service life, materials are recovered, reused, manufactured, remanufactured, or recycled rather than disposed of as waste. Climate responsive construction systems. Climate responsive design includes passive building strategies, energy efficient systems, renewable energy integration, water sensitive urban design, nature based solutions, resilient drainage systems, and low carbon materials. Then the technologies AI digital twins are becoming support are assisting climate responsive planning by analyzing environmental information, predicting future risk, and evaluating adaptation alternatives before implementation. Why traditional decision making is no longer sufficient is an important question. The traditional infrastructure, uh, the decision making frequently prioritizes one objective, which is to minimize construction costs or reduce project duration. However, sustainable infrastructure requires simultaneous consideration of numerous competing objectives. Decision makers need to evaluate environmental performance, economic feasibility, technical durability, social acceptance, resilience, resource efficiency, governance requirements, regulatory compliance, and long term operational performance. Improving one objective may reduce performance in another. For instance, materials with lower embodied carbon may involve higher initial cost but substantially lower life cycle impacts. Similarly, high resilient infrastructure may require greater capital investment while reducing long-term operational risk. These trade-offs show why modern infrastructure planning increasingly depends upon structured multi-criteria decision-making methods rather than intuitive judgment alone. Methodology, the recently published papers were considered on climate responsive system as well as circular construction systems. The case studies like Singapore, Finland, and Netherlands were taken into account, and such global case studies were connected to a multi-criteria decision framework in the context of circular construction and climate responsive systems. Role of multi-criteria decision making. Multi-criteria decision making provides systematic methods for evaluating the multiple alternatives using diverse sustainability criteria. Rather than selecting solutions based on a single indicator, multi-criteria decision making enables transparent comparison across environmental, economic, technical, and social dimensions. Among most widely applied methods are the analytic hierarchy process, analytic network process, TOPSIS, and so on. Within construction engineering, these methods support sustainable material selection, contractor evaluation, infrastructure prioritization, waste management planning, green procurement, and climate adaptation strategies. Integrating circular construction and climate responsiveness. Circular construction and climate responsive infrastructure should not be viewed as independent concepts. Instead, they represent complementary components of sustainable infrastructure systems, where climate circular economy principles reduce material consumption and waste generation, and climate responsive strategies improve resilience against environmental change. Then life cycle assessment evaluates environmental performance throughout infrastructure life, and life cycle cost analysis and assesses long-term economic performance. Then digital twins and AI continuously monitor operational performance and generate predictive information. Thus, multi-criteria decision making integrates all these dimensions into transparent engineering decisions. Emerging digital technologies supporting circular construction. To successfully implement circular construction at scale, digital technologies have become indispensable. Circular construction requires continuous information about materials, assets, environmental performance, and life cycle processes, something that traditional documentation systems cannot efficiently provide. The technologies which are necessary, like AI, which supports forecasting of construction waste, optimization of material use, prediction of component service life, and intelligent resource allocation. Then BIM, which provides digital representation of infrastructure and enables designers to evaluate material quantities, embodied carbon, and future adaptability before construction begins. Similarly, digital twins extend BIM by continuously integrating operational information collected throughout the infrastructure lifecycle, which enables engineers to monitor asset performance, evaluate maintenance strategies and support decisions regarding refurbishment or reuse. Similarly, IoT, GIS, blockchain, and cloud computing are also important in this context. Collectively, these technologies enable data-driven circular construction rather than isolated sustainability initiatives. Proposed multi-criteria decision-making framework. The first stage involves defining the infrastructure problem and identifying project objectives, which is step one. Then the second stage identifies relevant stakeholders, including engineers, policymakers, contractors, infrastructure owners, environmental experts, financial institutions, and local communities as the step two. Then the third stage establishes evaluation criteria, which include carbon emissions, life cycle costs, resource efficiency, circularity, climate resilience, durability, energy performance, social acceptance, governance maturity, and regulatory compliance. Then, in the fourth stage, which assigns weights to these criteria using recognized multi-criteria decision-making techniques such as analytic hierarchy process could be taken into account. Then the fifth stage evaluates alternative infrastructure solutions and sensitivity analysis are the six stages then performed to determine whether changes in a stakeholder prioritize significantly uh, influences the decision outcomes or not. And the final is step seven. The selected alternative supports transparent, evidence-based infrastructure planning. This framework improves decision quality before it explicitly considers multiple sustainability objectives simultaneously. Governance for circular construction. Technology alone cannot establish circular construction systems. So, governance provides institutional foundation that enables circular economy principles to be implemented consistently throughout the construction sector. Therefore, government policies establishes national circular economy strategies, building regulation, waste management, legislation, and sustainable procurement requirements. The industry governance promotes technical standards, environmental certification, professional guidelines, and quality assurance systems. So, project governance coordinates responsibilities among clients, designers, contractors, suppliers, and facility managers throughout the infrastructure lifecycle. The supply chain governance improves transparency regarding material origin, reuse potential, environmental performance, and circular material flows. And financial governance increasingly incorporates sustainability reporting, environmental disclosure, and green investment criteria. Uh, Case studies. Uh, the Netherlands is widely recognized as one of the global leaders in circular economy implementation. The Dutch government has established ambitious national objectives to transition towards a fully circular economy while it is significantly reducing dependence upon virgin raw materials. So, these initiatives have contributed to increased material recovery, improved resource productivity, and stronger integration of circular economy principles into national infrastructure development. Therefore, the Dutch experience shows that governance, procurement policy, and digital information management are fundamental drivers of circular construction. Then the case of Finland has integrated circular economy principles into infrastructure development through coordinated national strategies emphasizing resource efficiency and sustainable material management. The construction and demolition waste receives particular attention because these waste streams represent significant opportunities for material recovery. Then AI is increasingly supporting waste prediction and resource optimization through construction projects. These initiatives have strengthened recycling performance, improved resource productivity, and reduced dependence upon construction materials, fresh construction materials. Through the Finland, it shows that successful circular construction requires institutional collaboration supported by digital technologies and national policy. Then Singapore presents another important example because of its limited land availability and a strong commitment to sustainable urban development. The government promotes green mark certification to improve environmental performance through building life cycles. The construction productivity has enhanced through prefabricated, pre-finished volumetric construction, reducing waste generation while improving construction quality. So the Singapore demonstrates that regulatory leadership combined with digital innovation can accelerate transition towards circular and climate responsive construction. Results and discussion in Figure 1, it could be seen the growth of circular construction worldwide in the year 2025 is having uh, 167 billion US dollars, but by 2033 it is expected to reach over 375 billion US dollars, which is roughly twice the increase in market value in the span of 8 years. So it could be said that in the coming 7 years, the circular construction will increase in demand, and it will be wise to invest more in circular construction. But at the same time, multi-criteria decision making is also important in these systems. And in figure 2, it could be seen that climate resilient technologies is having a market value of 19.8 billion US dollar in this year 2026, but by 2033 it is expected to grow to 62.3 billion US dollars, which is uh, more than thrice increase in roughly 7 years. So it could be said that the climate resilient technologies will grow more in demand, and investment in them will be profitable. But at the same time, the multi-criteria decision making framework should be implemented so that uh, the climate resilient uh, infrastructure systems as well as circular construction systems could be complemented and successfully utilized. Then policy recommendation of the government should establish national circular construction strategies supported by measurable performance indicators, uh, green procurement policies, and incentives for low carbon materials. Then infrastructure organizations should adopt life cycle based planning rather than evaluating projects solely according to initial construction costs. And construction companies should strengthen digital capabilities through BIM, digital twins, AI, and material passport systems. And academic institutions should promote interdisciplinary education, integrating civil engineering, environmental science, data analytics, and sustainability assessment. The professional engineering organizations should develop technical standards supporting circular construction, life cycle assessment, and evidence-based infrastructure decision making. Together, these initiatives would strengthen institutional capability for sustainable infrastructure transformation. Then, future research directions should increasingly integrate digital technologies with sustainability decision making. AI has significant potential to automate waiting procedures, optimize the infrastructure alternatives, and improve predictive sustainability assessment. Similarly, digital twins, PIM, lifecycle assessment, and other advanced technologies must be investigated in future studies, particularly in emerging economies where infrastructure development is expanding mostly at a rapid rate. So, conclusion in this study, the concept of circular construction systems as well as climate responsive infrastructures were considered, and why multi-criteria decision framework is important in these systems. Then, through this study, the gaps in the existing literature were covered, and some global case studies, uh, which includes Singapore, uh, Finland, and other Netherlands, were incorporated, and how multi-criteria decision framework could be connected to these global case studies. In the case of circular construction, uh, were highlighted. Then the market growth and future scope of circular construction systems and climate responsive infrastructure systems with multi-criteria decision-making framework were explored. Thank you.